Hello students. So today let's try to understand what is binary search tree. So I think you have already understood the concept of binary tree. Initially we learned about linked list, uh, and even before that we learned about arrays, and initially we started with variables. So after variables we went through the concept of arrays in order to have elements of the same data type in a contiguous memory allocation. Then we understood that okay, we can use pointers and we need not have continuous memory allocations. We can simply create nodes and connect them with pointers. That really helps us because we get a very important advantage, and that is in case of arrays, when you create a particular array, the size is fixed and you priorly cannot determine what will be the exact size required for a particular application, right? So then the concept of linked list came, which actually got created from dynamic memory allocation. So initially it was dynamic memory allocation where we could allocate a chunk of memory for a particular storage of information. So after the linked list, then we had the concept of okay, instead of having a linear structure of elements, can we make it more dynamic, right? And with that came the concept of binary trees, or rather trees. So in the beginning it was trees, then a particular convention was made that okay, for a particular element two sub elements can be connected. Okay, so if you consider this particular element as a root node, then these are the children of this particular root node, and this root node will be termed as the parent, okay, with respect to B and C. So if we have this tree with us, then A is the root node, and C, for B and C we don't have any children, so they will be considered as leaves. Okay, in a tree we have leaves. Similarly, in case of data structures, in a tree we are going to have leaves. So if particular nodes do not have any children, then we are going to consider it as a leaf node. Okay, without any children means we don't have any next level here where these elements can have more elements connected to it. Okay, this is maybe level 0, this is level 1, and so on. So here you can see that after level 1 we don't have any elements, right? So we will consider B and C as the leaf nodes. Okay, so so this is a tree. Okay, this is a tree because we don't have any cyclic connection, which is actually the comparison between graphs and trees. In graphs we can have cycles, but in trees you cannot have cycles. Okay, so if you start from B, suppose, then you go from B to A, then to C, but you cannot again come back to B. All right, so after tree, it's a binary tree because every node can have maximum 2 children. Okay, so B has 2 children, sorry, A has 2 children, B has 0 children, and C has 0 children in this particular example. So yes, it is a binary tree. Okay, now if you consider binary search tree, then there is a little bit of change. Okay, this term search is going to put some importance, okay, put some speciality in the tree itself. So what is that? In case of binary search tree, which can also be termed as BST as an abbreviation, here this particular parent is going to have a higher value compared to the left child. Okay, again this particular parent is going to have a value which will be lower than the right child. So if you consider A, B and C as certain maybe numerical values, then we can say that A will be greater than B and A will be less than C. Okay, so A will be greater than B and A will be less than C. Okay, so if you go from left to right, the values will be in ascending order. So suppose A is suppose 5, and suppose this is B is suppose 1, and suppose C is 10. So 5 is greater than 1, but 5 is less than 10. And if you go from left to right, it will be 1, 5 and 10. Okay, it will be in ascending order. So if you do in order traversal, okay, if you put the in order traversal, then things will be in the ascending order. Okay, so then we come to a broader definition. So this was a simple explanation with 3 nodes, but suppose we have a very large tree with lot of elements. So here you can say that if we consider a particular node, okay, then its value will be greater than all the values of the nodes in the left subtree. Okay, again the value of A will be less than all the values of the nodes in the right subtree. Okay. So what it means is, what you mean by subtrees is there may be a group of nodes again that forms a tree. Here again we can have a group of nodes which can again form a tree, right, because it can keep on expanding, right. But in the end of the day, if you collect all of them and look at its values, you will find that all its values in the left hand side will be lesser than A, and if you consider all the nodes in the right hand side, those values will be greater than A. Okay, so here I have also marked it, values of this are less than A and values of this are greater than A. Fine. So BST is used because searching becomes faster, maximum of log n comparisons. Okay, so if you do linear comparison, then you have to do n comparisons, but if you go for BST, then you have to go for log of that particular value. Okay, so log of n. So n is the number of elements or number of nodes in a particular tree. Okay, so then we move to certain examples of binary search trees. So let's see how they are correct and how they are wrong. If you look at the first example, then we have 10, 5 and this is 2, I think. Let me expand it. Yes, it is 2. So if you consider these values here, you will find that if you look at any of the parents, their values will be following this particular convention. Okay, so if you look at 10, 10 is greater than 5, but 10 is less than 30. Again, if you look at 5, 5 is greater than 2. Again, if you look at 30, 30 is greater than 25, but 30 is less than 47. Okay, so if you consider any of the nodes, you will find that this convention is, or this particular rule is applied. Okay, so we have 2, 5, 10, 25, 30, 47, right? So if you go from left to right, the values will be like 2, 5, 10, 25, 30, 47. Alright, so it is a BST. It is a BST because first of all it's a tree, because you cannot find any cycle here, right? Then secondly, it is a binary tree because for every node we have 2 children. For every node you have maximum 2 children, sorry. You can have 1 children also, like in this case. Okay, you can have 0 children also, like in case of the leaves. So if you are asked how many leaf nodes are here, you will say there are 3 leaf nodes. Why? Because we have 2, 25 and 47. These are the nodes which do not have any children. Okay, so there are 3 leaves here. Okay, so please remember this. This is rightfully a binary search tree. Then let's look at this. We have 55, 20 and 19. So 55 is greater than 20, so it's fine. 20 is greater than 19, it is fine. So the rule has been satisfied. So it's a binary search tree. It's a tree, there is no cycle. It's a binary tree because every node has maximum 2 children. In this case we have maximum 1 children here, so it is fine, right? Because maximum you can have 2 children, so you can always have 1 children, right? So this is a binary search tree, no problem. Here it is a tree, yes, because we don't have any cycle. Then it is a binary tree as well, because if you look at each of the nodes, so look at 7 has 2 children, 20 has 2 children, 9 has 2 children, and 19, 25, 2 and 54 has 0 children. So maximum number of children for a particular node is 2. So it's a binary tree. However, it's not a binary search tree. Why? Because if you look at suppose 7 should be greater than this value, but this value is 20, right? So we cannot accept it. All right, though 7 is of course less than 9, however you have to have all the links proper, so we cannot accept it. Moreover, if you look at this entire collection of nodes, okay, something that we saw in this diagram, then if we consider all the nodes here, what are the values we have here? We have 9, 2 and 54. Now what it says is the parent, that is this 7, this value should be lesser than all the values inside the right subtree. Okay, but it is wrong, because 7 is not lesser than 2, right? So in this case also it is not satisfying the condition for a binary search tree. Okay, so I think from this example itself, we have your concept is clear about why I drew this diagram. Okay, so for example, let us take this subtree now. What are the values here? We have 19, 20 and 25. So all these values should have been lesser than this value, but it is not. In fact, all the values are greater than this value, so it is not going to be a binary search tree. All right, so let us move on. Let us take an example here. It's a binary search tree here. It satisfied all the conditions, because we have 1, 3 is lesser than 15, then we have 20, 17 which is greater than 15, then 50, 25, 70, 51, these are all greater than 21, so it is fine. In all the cases you will see that it is a binary search tree. Okay, now we told that the objective of binary search tree was to search, right, to search faster, but in fact the basic term here is searching. So how will you search for 20? So 20 may be present inside this tree, 20 may not be present inside the tree, but let's see what happens. So what happens is, when you are searching for an element, you always start from the root node. Okay, I think you already know what is the root node. So it is the first node in that particular tree from where searching begins. Okay, so there must be a pointer somewhere. Suppose name of the pointer is suppose first. Okay, from there this entire tree has been generated or created. Okay, so search 20. So how will you do it? First you will compare 20 with 21. If the value to be searched is lesser or lower than this value, then you go to the left hand side. Okay, so since 20 is lesser than 21, you go to the left hand side. Again 20 is greater than 15, so you go to the right hand side. Okay, so if the value to be searched is lesser than the particular node, then go to the left hand side. If the value to be searched is greater than the particular node, then go to the right hand side. Okay, so here 20 is lesser than 21, so you go to left hand side, then 20 is greater than 15, so you go to the right hand side, and then luckily you have found 20. So we were searching for 20, and we could have gone further, but here it is not required, because we have got a value which is equal to the value in the node itself. Okay, we were searching for 20, and while traversing through this particular tree we have found 20, so we will stop. Okay, so 20 is equal to 20, so we have stopped. Initially it was 20 lesser than 21, so we went left, then 20 was greater than 15, so we went right, and then we found the element. Now let us search for 47. So we will again start from 21. Since 47 is greater than 21, we go to the right hand side. Again 47 is lesser than 50, so we go to the left hand side. Okay, but we cannot go any further. So when we look at this particular value, 47 is not equal to 25, so we can declare that the element does not exist, right? We cannot go any further. We have found a particular leaf node here, so you cannot traverse anymore. Okay, so we will we are confirmed that this element does not exist. Okay, fine. Now let us go to the next concept of creating a binary tree. How will you create a binary tree? Okay, so suppose we have certain elements that will come in order. So first 40, then 60, then 50, then 33, then 55, then 11. Okay, these are some random values we have, and we want to create a binary search tree. Okay, so let us see how to be done. This first element will always be the root node. Okay, this first element will always be the root node. So we have 40 here, so we write 40 here. Fine. Then we have 60, so you compare 60 with 40. Since 60 is greater, so you go to the right hand side and put 60 here. Then we have 50, so again you start from the root node, you compare 50 with 40. Since 50 is greater, you go to the right hand side. Again you compare 50 with 60. Since 50 is now lesser, so you go to the left hand side and create the node 50. Then you have 33, so you compare 33 with 40. Since 33 is lesser or lower value, so you go to the left hand side and put 33 here. Then you have 55, so you compare 55 with 40 again. Then you, since 55 is larger, you go to the right hand side. Now 55 is lesser, so you go to the left hand side. Now 55 is larger, so you go to the right hand side and then put 55 here. And then for 11, since 11 is lesser than 40, you go to the left hand side. Again 11 is lesser than 33, so you go to the left hand side and put 11 here. Alright, so what you do is you take a piece of paper and whatever I just said, you try to do it on your own. Try to replicate the steps and try to construct the same tree. Okay, always remember, whenever a new element comes which has to be inserted, you always start from the root node. You always start comparison from the root node. Okay, so again we have an example here, 50. So 50 comes first, then 34. 34 is compared with 50. So since 34 is lesser, you put 34 here. Then we have 21. So 21 is lesser than 50. 21 is lesser than 34. So you put 21 here and so on. Okay, I will not repeat the same thing. So the same technique has been applied here to construct this particular tree. So I would request you to kindly try to do it on your own and see whether the output matches or not. You will find that all these elements in the left subtree of 50 are lesser than 50. All the elements in the right subtree of 50 are greater than 50. Okay, so 1, 21, 34, 37, they are all less than 50, and 51, 55, 90, 100, they are all greater than 50. If you take a smaller subtree also, like this subtree, for this subtree we can consider 55 to be the root node. Okay, if you only consider this particular tree, then 55 is the root node of the subtree. Now in this case also, all the elements in the left hand side will be lesser than 55. So 51 is lesser than 55, and all the elements to the right hand side of 55 will be larger than 55. So we have 90 and 100. These two values will be larger than 55. So you know, from any node you can draw a subtree. You can draw two subtrees and see whether that particular section or that particular portion of the tree is a BST or not. Okay, so no matter whichever subtree you take, smaller or larger, you will always find that the properties of a BST is followed. Okay, now we come to the concept of how to delete an element from BST. So we have created this particular tree here. This has been newly constructed. You cannot refer to a previous one. It's a newly created one. So here, suppose we have the elements, we have 52, 32, 25, 37, 35 and so on. Okay, and you will find that for any portion of this particular tree, the conditions of a BST is followed. Now suppose the objective is to now remove 74. Now how will you remove 74? Okay, because the topic is deleting an element from BST. So if you have to remove 74, then this space will become empty, and someone has to occupy this space so that the tree continues to exist, right? You cannot leave it empty. Okay, there always has to be an element somewhere, because if you remove 74, then this portion is broken and this portion is broken, or rather it is detached, right? You cannot have it detached, you have to join it. So what will you do for that? What can be done is, you can go to the left subtree and take the largest value. Okay, so you go to the left subtree of that particular element which will be removed. You go to the left subtree and take the largest value. So if you consider this subtree here, the largest value is 70. So you simply have to take 70 out from here and put it here. It is as simple as that. Okay, you go to the left subtree, take the maximum value and you put it in the place where the element has been removed. So I have written take the maximum value from left subtree. All right, so you, as you see here, this 70 has been taken and put here, so it will look like this now. Now does it continue to become a BST? Yes, it continues to become a BST, because if you look at 70, 61, 59, 53, 60, 62, 65, these all values are lesser than 70. And if you look at the right hand side, 78 and 85 are larger than 70. Okay, so see, even after removal of an element, we are able to maintain the condition for a binary search tree. Okay, here I have written that or minimum value from the right subtree. There is a convention you have, either you always take the maximum value from the left subtree, or you always take the minimum value from the right subtree. It is same. See, for example, in this case we had 74. Now suppose you take the minimum value from the right subtree, which is written in the brackets. If you take the minimum value from the right subtree, it is 78, so you can also take out 78, okay, and put it in the place of 74, and still you will find that the binary search tree is maintained. However, if you take the minimum value from the right subtree, you always have to take it, okay. So if I remove another element, even in that case you have to follow the convention with which you have started, okay. So either you always take the maximum value from left subtree, or you always take the minimum value from the right subtree, okay. So we will put some exercise problems to you. So I hope you come up with the answers, and I think that would be the best way to practice this particular concept. So with this, I would like to wind up for today. We will again join in the next class. Thank you.